What if we built a bridge across the Atlantic out of Lego? It sounds like a childhood dream, but for an engineer, it's a logistical nightmare involving 5,000 kilometers of plastic and a lot of salt water. Let's start clicking. To connect the bustling metropolis of New York with the historic charm of London, we'd need to span an approximate 5,500 kilometers. Now, let's talk bricks. If we design a structurally sound, albeit minimalist bridge that's a mere 10 meters wide, we're looking at a staggering 350 trillion individual Lego bricks. To truly grasp this number, imagine stacking these bricks in a single column. That column would reach the moon and back, not once, but roughly 15 times over, perhaps even tickling Mars on a good day. Of course, long before that, the bottom bricks would have fused into a diamond-hard, unidentifiable polymer from the immense pressure. The Lego Group, a titan of plastic production, manages to churn out about 75 billion bricks annually. This means if we were to commandeer every single Lego factory on Earth and demand that every citizen halt their construction of intricate Millennium Falcons, Death Stars, and quaint little Lego Friends villages, our project would still take over 4,600 years to simply amass the raw materials. By the time our diligent, future human construction crews even began to celebrate the completion of the European side, the American side would have long since succumbed to the relentless forces of erosion, UV degradation, and simple existential dread, crumbling into a vast, oceanic soup of microplastics. Essentially, we wouldn't be building a bridge, we'd be constructing a 5,000-kilometer-long, slowly dissolving transatlantic environmental disaster. A marvel of engineering? More like a monument to hubris. The Atlantic, far from being a flat, placid surface, is a colossal basin with an average depth plunging to a staggering 3.6 kilometers. Our primary building material, ABS plastic, boasts a density of about 1.04 grams per centimeter cubed, just marginally denser than the surrounding seawater, which hovers around 1.025 grams per centimeter cubed. This seemingly minor difference is critical. Due to the omnipresent air trapped within the hollow studs and internal structures of each Lego brick, our colossal bridge, defying all conventional expectations of a solid structure, would possess an alarming tendency to float away like a gigantic, brightly colored piece of confetti caught in a breeze. To counteract this buoyant defiance and anchor our plastic leviathan, we are presented with two equally daunting and absurd choices. Option 1. Meticulously fill every single hollow cavity of every single one of those 350 trillion bricks with lead. This would not only necessitate an unimaginable budget, causing the global lead market to collapse under the sheer demand, but would also turn our whimsical bridge into a toxic environmental nightmare. Option 2. Rely on lithostatic squashing. At the crushing depths of the Puerto Rico Trench, where pressures can reach up to 800 atmospheres, the sheer, unimaginable weight of the water column and the millions of tons of Lego bricks above would exert such immense force that the bottom layers wouldn't merely be bricks anymore. Instead, they would be compressed, heated, and ultimately fused into a semi-liquid amorphous plastic sludge, a kind of geological-scale lava lamp. This foundation would be less a feat of engineering and more a testament to the destructive power of pressure, resembling a bizarre, multicolored tar pit at the bottom of the ocean. While Lego bricks are lauded for their legendary clutch power, that satisfying click and secure hold, they were definitively not engineered to withstand the complex, gargantuan forces of the Coriolis effect, seismic shifts, or, most critically, the relentless thermal expansion and contraction over thousands of kilometers. On a blazing summer day, exposed to direct sunlight, the plastic temperature could easily soar by 30 degrees Celsius. According to the immutable laws of physics, this temperature increase dictates that our entire 5,500-kilometer plastic behemoth must expand. Over such an immense distance, this seemingly minor thermal change would result in the bridge's total length increasing by several kilometers. Without meticulously designed, massive, and incredibly complex expansion joints every few hundred meters, the bridge would have nowhere to dissipate this incredible internal stress but upwards. It would buckle into a gargantuan, awe-inspiring arc, potentially reaching the lower stratosphere, transforming into the world's most expensive and least practical plastic roller coaster. Imagine attempting to drive your car up a perilous 20-degree plastic incline, only to encounter a sudden, yawning gap where a brick simply popped out due to the sheer, unyielding stress. You wouldn't just be undertaking a transoceanic journey, you'd inadvertently be participating in a low-budget, highly precarious space program. Furthermore, a single loose stud, a seemingly insignificant flaw in the middle of the Atlantic, could initiate a catastrophic chain reaction, effectively unzipping the entire colorful plastic zipper stretching across the horizon, sending trillions of bricks cascading into the abyss. The North Atlantic is far from a serene pond. It's a perpetually chaotic mess of corrosive saltwater, relentless winds, and monstrous 20-meter waves that can make even steel-reinforced ships feel insignificant. While a single humble Lego brick is remarkably tough, capable of surviving being chewed by a dog or swallowed by a child, don't try this at home, a bridge constructed from trillions of them is essentially a 5,000-kilometer-long, utterly impractical sail. The lateral force exerted by a hurricane-strength wind would apply millions, if not billions, of newtons of pressure across the entire structure. Since Lego is held together primarily by the miraculous yet ultimately limited power of friction between interlocking studs and not by robust chemical bonds, the entire bridge would inevitably begin to vibrate. At a certain resonant frequency, perhaps triggered by a particularly strong gust or a rogue wave, the legendary clutch power would finally fail. We would then bear witness to a truly spectacular and profoundly depressing phenomenon. The bridge would begin to dissolve from its edges, systematically shedding millions upon millions of 2x4 bricks into the powerful ocean currents. Within a matter of weeks, every single beach stretching from the sunny shores of Florida to the rugged coastlines of Scotland would be inundated, buried under a knee-deep layer of brightly colored but utterly hazardous plastic debris. The infamous Great Pacific Garbage Patch would finally acquire a much more expensive, vastly more absurd, and entirely Atlantic rival, forcing future generations of sea turtles to somehow evolve to navigate or even incorporate 90-degree corner shells into their anatomy. If by some miraculous oversight the Atlantic's furious weather somehow fails to dismantle our plastic masterpiece, the ceaseless march of traffic will surely finish the job. Every time a car tire rolls over the slightly raised surface of a Lego brick, it causes a minuscule compression and a tiny, almost imperceptible micro-movement between interlocking studs. In a structure composed of 350 trillion individual bricks, each of these micro-movements generates a minute amount of energy, which is then dissipated as heat through friction between the plastic surfaces. With thousands of vehicles, from compact cars to heavy-duty trucks, crossing every single hour, this cumulative frictional energy would translate into a significant and ultimately catastrophic rise in the internal temperature of the bridge. ABS plastic, our heroic building material, begins to soften and lose its structural integrity at a relatively low temperature of around 105 degrees Celsius. In a high-traffic scenario, especially during peak summer heat, the core of the bridge would rapidly transform into a literal zone of forbidden taffy, a gooey, semi-molten stretch where the bricks lose their legendary grip and begin to sag under their own immense weight. Imagine driving merrily along only for your wheels to suddenly sink into a squishy, melted Technic beam, bringing traffic to a standstill and perhaps causing a multi-vehicle pileup in the middle of the ocean. The bridge wouldn't snap dramatically. Instead, it would simply droop into the ocean like an enormous, multicolored piece of overcooked spaghetti, slowly, inevitably, and tragically dragging the entire global economy down with its plastic collapse. Beyond the grand existential threats of physics, we must address the most immediate and visceral danger: maintenance. A project of this unprecedented scale, Spanning thousands of kilometers of hostile ocean would necessitate constant, meticulous inspection and repair. But here lies the true Achilles heel of our Lego marvel. The bridge's surface is, by its very nature, an inherently uneven, relentlessly studded terrain. It's not a smooth paved road. It's a 5,000-kilometer-long minefield specifically designed to inflict maximum pain. If a maintenance worker, diligently traversing this plastic gauntlet, were to lose their shoe, tragically common occurrence in high-wind, exposed ocean environments, they would immediately face the most excruciating, soul-crushing agony known to humanity, stepping squarely on a single, innocent-looking Lego brick with a bare foot. This seemingly minor mishap, universally acknowledged as a form of torture, exerts a staggering 3 million pascals on a tiny, vulnerable area of skin. In the desolate, isolating expanse of the mid-Atlantic, thousands of kilometers from the nearest emergency room, this isn't merely a nuisance or a fleeting moment of discomfort. It swiftly escalates into a critical, life-threatening medical emergency. We would inevitably be forced to construct a parallel, structurally dubious safety bridge out of giant, child-friendly Duplo bricks, solely for the purpose of safely transporting the endless stream of injured workers, effectively doubling the monumental cost and tripling the profound embarrassment of the entire global engineering community. So, after all these meticulous and frankly somewhat alarming calculations, the burning question remains: is a Lego Atlantic bridge even remotely possible? Technically, if we possess the boundless, unshakable optimism of a 6-year-old, coupled with an almost criminal disregard for basic economics, the immutable laws of thermodynamics, and perhaps a casual dismissal of the Geneva Convention concerning environmental waste, then yes, theoretically, it could be constructed. However, the end result would be far from a grand marvel of modern transport. Instead, it would stand as a 5,000-kilometer-long, multicolored monument to humanity's most ambitious, yet ultimately misguided engineering folly, a permanent plastic testament to precisely why we universally opt for materials like steel and concrete for such undertakings. In the inevitable grand finale, the bridge would almost certainly be slowly, meticulously, and rather pathetically reclaimed by the merciless forces of the sea, leaving future, more sensible civilizations to ponder with bemused bewilderment why the ostensibly intelligent humans of the 21st century felt compelled to pave an entire ocean with children's toys. We would be immortalized in history not as visionary builders, but as the audacious, perhaps slightly unhinged, people who succeeded in making the vast, majestic Atlantic Ocean marginally more colorful, infinitesimally more prone to thermal deformation, and immeasurably more painful to walk on barefoot. But hey, on the undeniably bright side, we'd finally, unequivocally, and permanently have a perfectly legitimate, if utterly impractical, use for all those perpetually multiplying, infuriatingly small, spare, flat one-by-one pieces that seem to spontaneously generate in everyone's junk drawers and under every piece of furniture across the globe.